Hello, I'm Mansi Limbu. In this video, I'll be presenting my paper on team coordination on graphs with state-dependent age costs. We will begin by understanding the problem formulation. Imagine a complex graph environment where multiple rovers must reach a specific goal. However, the path is not straightforward due to multiple risks involved. These risks can be mitigated if a robot receives support from a teammate, enabling the robot to take actions that minimize traversal cost to the goal. To accomplish this, we developed a specialized graph known as joint state graph or JSG. We can transform given environment graph incorporating the idea of the risks, edges, and support nodes to a new graph JSG. In JSG, nodes represent the various joint state, edges symbolize the feasible transition between these joint state. The cost associated with each edge is aggregation of the individual action cost for each robot involved. JSG has three kinds of edges: regular, risks, and support edges. While JSG regular edges has original edge cost, risk edges has high cost if the robots traverse through them. Support edges on other hand has reduced cost due to the support from a teammate. Once the complete JSG is constructed, we can run a path planning algorithm from the joint start nodes to the joint goal nodes, which are 1, 1 and 5, 5 respectively. We see both robots jointly navigate the minimum cost path to reach the goal using supporting behavior. Here is another example of JSG path planning in more complex graph. One main problem with JSG is that it becomes more computationally inefficient as the environment graph becomes more complex with increasing nodes and risk edges. To improve upon the JSG limitation, we come up with a new hierarchical approach called CJSG or critical joint state graph. In CJSG, we split robot movements into two types, coupled and decoupled. Coupled movements use support graph for coordinated actions to reduce cost. On the other hand, decoupled movements are planned individually by each robot on a base graph where no coordination is needed. In CJSG, nodes represent critical joint state where robots can either initiate or complete support action in addition to the joint start and joint goal nodes. Each cost account for robots' movement with the base graph or movement in potentially lower cost edge due to supportive actions. It is important to note that CJSG is fully connected here. We can see an example of the path planning using CJSG here. We see both robots jointly navigate the minimum cost path to reach the goal using coupled and decoupled actions. In our experiment, we evaluated both of our contributions, JSG and CJSG, in terms of graph construction time and shortest path planning time in seconds, as illustrated in the table. We conducted these comparisons by incrementally increasing both the number of nodes and then the ratio of the risk edges to the total edges in the same graph. We list our results in this table. We then plot the results in this graph. The graph shows CJSG significantly reduces computational time for both graph construction and path planning compared to JSG, confirming its efficiency in generating total solution. To summarize, our work aims to optimize team coordination among multiple robots in graph environments by incorporating the concept of risks and support. We initially transform environment graphs into joint state graph JSG by accounting these factors. Next, we introduce critical joint state graph CJSG, which is computationally efficient alternative to JSG. Experimental results demonstrate that CJSG is both faster in graph construction time and path planning time than JSG.